All right, so we just figured out that in order for this object to make a perfect circle, in other words, to orbit the Earth, it has to have a speed that, right? We just figured that out. So that means if you were out in deep outer space and you had a ball or a car or whatever you want, if you could give it that speed, it would make a nice circular orbit around the Earth. All right, now earlier we learned this, right? For a circle, the velocity is distance over time, but if the time is the period, that's the time for one orbit. So the distance for one orbit is the circumference. So this equation is true generally, and this equation is true for this particular problem. So what I'd like you to do now, because you need practice in algebra, I'd like you to put this equal to this and then solve for t squared. So please pause your video and do that. Okay, so I'm assuming you did it. Let's do it together. So we have 2 pi r over t equals square root of g m over r. So let's just solve for t. So we're going to flip it. We'll just solve for t, right? So basically, so t is equal to 2 pi r over, multiplied by square root of r over gm. Correct? Well, what is that? So we have 2 pi r. Now this is r, this is a half. So that's r to the 3 halves divided by square root of gm. Now that's t. I said solve for t squared. So therefore, t squared equals 4 pi squared r cubed all over gm. Now, you're saying, whoopee, what do I care? Well, if you ever take an astronomy class, you'll learn about Kepler's 3 laws of motion. And this is Kepler's 3rd law of motion. So we just figured out Kepler's 3rd law of motion. Now the neat thing about this, Kepler did this before Newton. And so Kepler, he didn't have Newton's laws of motion. He just had a lot of data. So he just analyzed data and he came up with this. And then later on, Newton came along and he figured out the, Newton's law of gravity. It wasn't called that at the time, of course. And then, so you just use Newton's law of gravity and bingo, there it is. So that was kind of cool that they came up with the same equation. One using just data, Kepler, and this way just by using Newton's law of gravity. All right, we want to do one more problem with the centripetal force. And this is a great problem. So everybody read it, please. All right, what is the normal force acting on a car when the car is on the top of the hill and at the bottom of the valley? Now, we have to make some approximations here. All we've been learning about is circular motion. So what are we going to say is true about the top of the hill? It's circular, all right? What are we going to say at the bottom of the valley? It's circular, okay? Because what else can we do? All we've been studying is circular motion. All right, let's do the hill first. All right, sum of the centripetal forces equals mv squared over r. As I say over and over and over, it's always true, so you write it down. But then what you have to do is you have to figure out what those centripetal forces are. Well, what are the centripetal? I can't write on the screen, I wish I could. What are the centripetal forces here? Well, what's acting on the car? When the car's at the top of the hill, what are the forces acting on it? Gravity, which points towards the center of the circle, and normal, which points away from the center of the circle. So as we discussed in the past, mg points towards the center of the circle, so it gets a plus sign. The normal points directly away from the center of the circle, so it gets a minus sign. So that's why it says mg minus n. So you look at this, and you conclude that the normal force equals mg minus mv squared over r. There you go. All right. Now, let's do the valley. Valley. Okay, as usual, sum of the centripetal forces equals mv squared over r. So you just write it down because it's true. Now, now here, what are the forces on the car? There's a normal that points towards the center of the circle, and there's weight that points away from the center of the circle. So here, the normal is positive, and the weight is negative. So therefore, the normal equals mg plus mv squared over r. There you go. So I like that example because it emphasizes the use of the plus, the pluses and the minuses, all right? Okay. Let's review. All right, so again, don't forget, we still have more to do on a later chapter on non-uniform circular motion. But anyway, uniform circular motion, orbits, and gravity. We extended our understanding of kinematics of circular motion beyond the basics. Yeah. We applied Newton's laws for circular motion. Yeah, we sure did, right? Newton's law right there. Sum of the forces equals mv squared over r. We talked about the orbits of satellites and planets. And we talked about the long range force of gravity. That's the Newton's law of gravity. Long range force. I mean, why does the Earth circle the sun? Because of that long range force of gravity. Okay, let's review. If this is uniform circular motion, there has to be a centripetal acceleration that changes the direction of motion. And we've seen that many times. The velocity is always perpendicular to that centripetal acceleration. I would memorize this, honestly. A sub c equals v squared over r. You're going to see it again and again and again. It's not too hard. This is that nice formula for a circle. Okay, velocity, distance over time. For a circle, if we make the time the period, which is the time for one orbit, the distance has to be the circumference of the circle, 2 pi r. And that's equal to 2 pi rf. So whatever, this one or this one, whatever the problem requires, you use it. Okay, whenever there's circular motion, there's going to be a centripetal force. Sum of the force equals mac, which equals mv squared over r. But again, your job is to figure out what are the centripetal forces. That's your job, or our job. That's Newton's law of gravity. And we're done. See you later.